Hello everyone, my name is Xinyang and I am a rising senior at the University of Wisconsin-Madison. Today I will present about the ML degree of encyclical models. My presentation will be in two parts. I will first introduce the problem, give some definitions, and then state the main result. Next, I will illustrate the results by using an example about the scaled binary for cycle models. The problem we want to investigate is to find the maximum likelihood estimator of a given model, which is a probability distribution that maximizes the likelihood function. This is a fundamental optimization problem in statistics, and we want to approach this problem in the view of algebraic geometry. There are many existing approaches. For instance, the multi-regeneration method solves this problem in an algebraic way. The EM algorithm, which is commonly used by statisticians, solve this problem in a hill climbing method. However, both methods face some difficulties. The first one may have a long running time because, as we can see in later slides, the number of critical points grow very fast. It can easily get to a 5 or 6 digits number. For the EM algorithm, it doesn't know whether it has already found all the critical points, so it doesn't guarantee to find the true maximizer of the model. As we can see, both methods have the following concept. It starts with finding all the critical points and then select the MLE from them. We want to approach this problem in a different concept. We start with a MLE of a scaled version of the model we want to investigate and track the change of the MLE as we continuously deform the scaled version back to the original one. Now let's give some definitions. A statistical model maps data space to probability space, and a project will mainly study the binary encyclical models, which is a family of discrete exponentials which are commonly used to express conditional independence among variables. Also know that when n is bigger than 3, this model is non-decomposable, which means that it generally does not have a closed form MLE. The ML degree is the number of critical points of the likelihood function of a statistical model, and the MLE is one of these critical points. And Mendela introduced the family of scaled models, which scales each entry of the probability vector by a complex number. Scalings are very useful because, on one hand, it can change the amount of ML degree, and on the other hand, we can use homotopy to go from a scaled model to another one. Houston, Catan, and Stanford gave the upper bound, which is also the ML degree of generic scaling in the following theorem. As we can see, the ML degree grows very fast. However, if we can find some net scalings, we can decrease the ML degree by a lot. This is because when we are applying homotopy to go from a generically scaled model to some special one, some of the critical points will go off to infinity and therefore they will not be counted in the ML degree. And now we want to ask this question. How do we get the ML degree down to 1? We want this because when we only have one critical point, the MLE is there for that point, and we can express it using the data vector U because it is a sufficient statistic. This leads to our main theorem. For any binary encyclical model, we define a vector Cn using this formulation, and we prove that the model scaled by this vector admits Kapranov's Horn uniformization, and therefore it will have ML degree 1 with generic data. This critical point is therefore the MLE, and we also develop a closed form expression of this MLE. The homotopy tracking algorithm is based off the main theorem. We calculate the MLE using the theorem above, which is very fast because it is in the closed form, and then we set it as a starter point x0. Then we use homotopy to deform the Cn scaled model to any model we want to investigate and trace the change of x0. The final destination of x0 is therefore the MLE of the desired model. This method is fast because it avoids computing all the possible critical points, which is a huge number in most of the cases. And it also guarantees to find the true MLE. Here is the pseudocode for running the homotopy tracking algorithm, and we will use Macaulay 2 as our programming language. We developed 4 generators. To write C start, which is the Cn in the theorem, the A matrix, which encodes the binary n-cycle model before scaling, and the Horn matrix, and we use these 3 results to compute the MLE start, which is the MLE of the Cn scout model. And then we apply homotopy to trace the final MLE of arbitrary scout model. Next, let's see an example when n equals 4. There are 4 random variables x1 through x4, with each of them has 0 and 1 as the possible outcomes. The edge is used to indicate the conditional independence. As we can see, x1 and x3 are independent given x2 and x4. x2 and x4 are independent given x1 and x3. We parameterize a probability Pijkh using the function psi indexed by the value at ij, jk, kh, and ih. This parameterization is indicated in the matrix A. And we scale this probability vector with a vector c of length 16. Recalling the formulation of the spatial vector Cn in the main theorem, we write down the C4 in this case. And we claim that this C4 scaled model gave ML degree 1. We will prove this using Hall's theorem by showing that the model admits the Horn uniformization. H4 is the Horn matrix generated by the algorithm that we developed. Using H4 and C4, we define a Horn map that maps the projected space of the data dominantly onto the probability space of the C4 scout model. By definition, this model admits the Horn uniformization, and therefore the Horn map psi is the MLE of the model. Here is a comparison of the running time between multi-regeneration method and our method. For an arbitrary binary 4-cycle model, we cost less than 0.2 seconds, but the multi-regeneration method needs almost 2 minutes. We will continue this project in the following directions. First, we will apply the same idea to different statistical models. Secondly, we will try to further optimize the running time by optimize the generators and also the homotopy algorithm. I want to say thank you to Jose, my amazing mentor who gave me a lot of support in this project. And this concludes my presentation, and thank you for your attention.